The problem is basically the interface.
Well, they basically force feed you Google Plus.
Mm.
That is very good change.
Yeah. Very drastic management adjustments. I'm going to switch to one that use contrast. Let me just make sure this is. Just let me I want to make sure that. Oh, I don't think it goes here. It's not because of, I don't think it's a protocol. We need a backup. Is this all set up and working? Oh. Yeah, can you focus on Xavier? Thank you.
Underrated light from this TV show as the water cards. Any kind of president. This is the Netflix TV show. As a 2016. It is really cool.
So you may have to speak. I didn't use the microphone. Some people like it. So these are all like this. Oh, okay. Yeah. I mean, I'll. Good. Are we on? Please.
Not yet. When you're ready.
No, let's use a different battery. Okay. And that works. And this is what CPU usually has. Okay. Yeah. Okay, so it's a great pleasure to have, as one of the highlights of the summer school, Xavier Amatrain here, and I hope I kind of got his name approximately right. So if you were ever wondering why you see on Netflix what you see in terms of recommendations, is the map. So he has a great team there, and well, my guess is it's one of the reasons why Netflix is so popular. So I'm really looking forward to his tutorials today and tomorrow. And yeah, take it away.
Thank you, Alex. Yeah, thank you for having me here, and it's a great pleasure. I would usually not give a lecture with a baseball cap, but you know, we just changed the Netflix logo, and this is the first swap that I got with the new logo. So I said, since I'm on camera, I'm going to be wearing it. And I also, the other thing I wouldn't do is to give a lecture with some kind of political statement like I have here, like Underwood 2016. Do people know who Frank Underwood is?
Yeah.
Yeah, from House of Cards. Yeah, so I'm a big fan of House of Cards, one of the Netflix originals, so that's why I thought it would be good to do the lecture with this T-shirt. So I'm going to get started, and I'm going to be talking about recommender systems. I'll first maybe let me start by saying that I know there was another lecture by Deepak some days ago on a related topic. I'm happy to say that we coordinated well, and I know what he talked about, and I'm going to be complementing some of the things he talked about. I'm going to also be probably introducing some of the topics that he didn't mention, so that's all going to be, I think, interesting for all of you. And I am going to also be giving you a little bit of a practical examples coming from Netflix and other companies. Sorry. Make sure that I have my, I don't have power here, so it's going to be.
You need audio?
No, I need to plug in the laptop somewhere that.
Yeah.
You know where that would be, because otherwise it's going to be going into sleep mode all the time. Okay, so first of all, I thought I would get started with a little bit about telling about who I am and how I got to be at Netflix and work on recommender systems, which is kind of a long story. I've been doing research for almost 20 years now, but I'm originally from Barcelona, Spain. That's why my name Xavier is a little bit complicated to pronounce. And I did my PhD, interestingly, working on things related to signal processing and large-scale distributed software systems, particularly in the domain of audio and music. So I was in some research group that's called Music Technology Group, and I developed, among other things, a pretty popular open source framework that's called CLAMP for developing large-scale and real-time audio and music applications. So that was back then. And then I moved and I became research director at UCSB. At UCSB in Santa Barbara, I evolved a little bit and worked on, again, large-scale multimedia systems, but I was working on immersive virtual reality environments. I directed a project that's called the Allosphere, which is a huge immersive environment at UCSB. And then I went back to Barcelona after being in the US for a couple of years, and I went into a research lab for Telefónica. Telefónica is one of the largest phone companies and communication companies in the world. It's actually, I think, the third or fourth. And I was doing research there, and there I really went back to something I had done during my PhD, which was machine learning, recommendation systems, information retrieval, and so on. So I was there for 4 or 5 years working on research related to these topics. And after that, I moved to Netflix, and I've been there for 3 years. So now I'm the director of something we call Algorithms Engineering Team. And what we do there is basically develop all the algorithms that drive the personalization, the recommendation, also search. So all those algorithms are something that my team is working on. Okay, and here are some publications that I've worked on. I'm not going to do the kind of tutorial that I'm going to push a lot of my publications into the tutorial. I'll be talking about a couple of them, like tensor factorization, for example. But if you look me up in Google Scholar or anywhere, you'll see some of these publications, most of which, the latest ones since, say, 2000 and something, are related to machine learning recommendations and information retrieval. Okay, and some of the people that have contributed to this tutorial, so Justin is a manager in my team, he's with Netflix. Alexandros, who worked with me in Telefonica, and we've actually exchanged slides for similar tutorials that we've done at different schools. Bamshad at DePaul University, we're going to be giving a tutorial in KDD in New York about recommendations, and we've been preparing that tutorial, and part of these slides are going to go into it. And Francesco Ricci, a good friend, professor at University of Bolzano, very well known in the field. And Eric from Spotify, I basically put him out because I grabbed something that he recently published in a blog post, and I'm going to be talking about how they use deep learning for recommendations. I'm also going to be talking about how we use it for recommendations. Okay, so here is the outline of what I'm going to be talking about. And I have a lot of slides, a lot of topics to cover, and maybe if I get enough interaction, enough questions, which would be ideal. So I forgot to mention this, so please interrupt me, ask me questions. Maybe we won't be able to cover everything, but I've done it in such a way that I think the most important topics are going to be covered first. And if we don't get to, say, the practical example in Netflix, I've been talking about that many times in the past, and you can probably find videos in video lectures or YouTube where you're going to get a similar flavor of that. So it wouldn't bother me too much if we don't get there. So I really encourage you to ask questions during these 2 days. Okay. And before I get to even to the introduction, when you give a course like this, it's always a challenge to understand who you're going to have in the audience, right? Because they're going to be all over the place, people from undergrads to people that are doing research in the field, and then I'm trying to adapt the slides that I have in a way that the introduction is going to be very gentle, and then I try to get deeper into other topics as we advance in the course. But I'd like to have an initial sort of show of hands to give me some idea of who I have in the audience. So, for example, how many of you are undergrads? No undergrads? PhD students? Okay, so the ones who raised your hand. PhD students in computer science? Okay, so most of them. How many of you are postdocs or researchers? Industry folks? Is there anybody from industry? Oh, yeah, okay. Okay, great. So I hope to meet many of you during the breaks or in some of the activities, but I get a sense of more or less who I have in the audience, which is good for me. Okay, so let me get started. And again, I know that Deepak talked about recommendations and about some of the algorithms. I saw his slides, and I think I felt that I could also give a different flavor of justification of why recommendation is important and what does it mean from both an academic but also an industry perspective. So I'd like to start with these 2 quotes that I think are pretty relevant. Chris Anderson, in a very popular book, The Long Tail, said something that struck me as interesting. He said that we are leaving the age of information and entering the age of recommendation, right? And he was saying that in the context of this information overload and how much information we have, and the idea that having information is great, but unless you have a way to filter it out and to get to the important things, it's pretty much useless, right? And this other quote from CNN Money is very similar, right? Where it says we're leaving the era of search and we're entering one of discovery, which is pretty much related to recommendation. So discovery is not when you're looking for something explicitly, when something that you didn't know it existed, it actually finds you. And I've been for a long time giving this idea of search versus recommendation, and the idea that basically, I mean, they're 2 sides of the same coin, and in search, the only difference is that you have an explicit query. In recommendation, that query is implicit, and it's basically made by the user and the context, right? Many methods are shared, many are specific to recommendation, but there's really a very thin line between, say, personalized search and recommendation. And again, the difference is that you don't have an explicit query. And when we talk about information overload, I've been using this quote from November 2006 for years, and it was saying that people read around 10 megabytes of material a day and hear 400 megabytes and see 1 megabyte of information a second. And I wanted to update it for the tutorial this time, and I looked it up, and I saw there was a study from this year from UCSD, and their prediction, which is almost, it's a very short time prediction, next year, right, 2015, the consumption, and that's per user, per person, is roughly 74 gigabytes of information a day, right? So when we're talking about the amount of information that is being consumed, not to mention the amount of information that is available and not consumed. A very interesting book here by Barry Schwartz, The Paradox of Choice. He gives a lot of examples, a lot of experiments done on consumer preferences and consumer sciences of why having more choices it's not always a good idea. So I think the most quoted example, and there's a video of Barry talking at Google precisely about this. It's one in where a shop, they had to sell some different flavors of jams, and they did an experiment. They put 6 different flavors, and they had so for people to come in and taste them, and they could taste them and buy them, of course. And then they did the same experiment, but instead of 6 flavors, they put 64 flavors. And the result of the experiment was, interestingly, that when there were only 6 flavors available, people bought much more than when they had 64. And what's the conclusion there? The conclusion is that people get overloaded when they see a lot of choices, and making choices has a cost, and at the end of the day, people decide not to act just because they have too many choices to make, right? So we need to, if we want people to act, to make decisions, we need to narrow the choices and make their life easier, and that's what recommendations will do for you. Okay, so value of recommendation in Netflix, roughly 2/3 of the movies and TV shows that are watched are recommended. I think now we're up from that to roughly around 80% of the things that people watch come from some sort of recommendations. And even when people search, which is not, we don't consider it a recommendation, we do recommend things. I'll talk about that when I talk about the practical example of Netflix. In Google News, they published that when they introduced recommendations, they got 38% more click-through. Amazon, 35% of the sales come from recommendations. And ChoiceStream had a study where they found that if people had, if people would buy 28% more of the music if they really found what they were looking for. So all of this is about the sort of commercial and value that recommendations have for industry and for companies. And that's why it's a hot topic, and that's why you have 2 lectures in this course about recommendations, because it's something that it's based on machine learning algorithms, it's based on something that probably you guys are studying, but it's also very interesting and very relevant for companies and industry. Okay, so what is what we call the recommendation problem? And this is has been cited and quoted many times. So the recommendation problem, we describe it as a utility function that is trying to estimate or predict how a user will like an item, right? And this is a very generic definition, and we'll get more into some instances of this definition. And what this prediction is going to be based on depends on what we have, right? It can be based on past behavior, and that will get us to collaborative filtering. It can be based on relation to other users, and we can talk about social recommendations, for example. It can be based on item similarity. You can do content-based recommendations based on that. It can be based on context, and many different things, right? So depending on the kind of information that we have available, we'll address it as a different problem and use different methods. So more formally, if we have C be the set of all users and S be the set of all possible items that we can recommend, right? So basically our utility function U is going to be a function that measures the usefulness of some items S to the user C. And R, the subset of S that we will be recommending, is a totally ordered set. And totally ordered is also an interesting concept that we'll be getting to when we talk about learning to rank and how we use learning to rank approaches for recommendations. But the basic idea is that we need to be able to order things, because at the end of the day, recommendation, just a search, is a way to order things in using some utility function in a way that you can prioritize some things versus others. And of course, for each user, we want to choose a subset of items in S that maximize this utility function. Okay, so any questions so far? No? So another way to look at, yes?
That's at one instant of time, the recommendation.
It is, yeah. It is at one instance of time. And I will be talking slightly about how time matters in this definition, but not too much. But I have a publication about the importance of time as a way to, how to incorporate the evolution of time into this kind of formulation. So another way to look at this, and actually this is a way to look at many of the sort of machine learning-based applications, is as a two-way process. We usually have two parts or two different processes that happen when we do the recommendations. We have an offline component, and the offline component may happen or not, depends on the model that you use. But basically, there is a learning process in which you may have users and items, and you're building some kind of model, some kind of clustering approach, for example. And then online, you have some context, and you have a decision process, and then you recommend the items, right? The trade-off between how much you do offline and how much you do online, depending on the method, that's something that, again, I won't get too much into it, but it's pretty relevant, especially on practical applications of deciding what method makes sense and how does it make sense. Depends a lot on how much you decide to do offline and what you need to do online, right? So for example, if you follow, let's say, any sort of map-reduce approach, you're going to be doing a lot of work here on the offline world. But however, incorporating context from a real-time application and context like the location or the time is going to be more difficult. Okay, so just a brief summary. We'll get into all of this, but just to get started, brief summary of recommendation approaches. So collaborative filtering, that's the one we're going to be spending most of the time on. So collaborative filtering is when we recommend things based only on past user behavior, right? So this approach is basically agnostic to what you're recommending. You don't need to have any domain expertise per se. So you don't need to know if you're recommending books, movies, music, or a car. And the idea is that you're going to be leveraging the relation between users. Some people get confused because there's two kinds of collaborative filtering approaches. We'll go into the user-based and item-based. Neither of them needs to have any information about the item, right? So the item-based approach, we will be making recommendations based on the similarity between items, but that similarity is going to be based only on past user behavior. So basically, we're going to be leveraging what users did in the past to infer a similarity function between items. On the other hand, content-based, that's the opposite. So here, we don't care about what the users did, and we based completely our approach on the domain knowledge, knowing what the items are, what they mean, and trying to find functions, usually similarity functions, that describe items as similar based on the content, so based on the description of the item. Personalized learning to rank, you will not, in sort of like traditional tutorials on recommendations or books, you won't see this as a first-class citizen in the recommendation approach. I've been saying for a couple of years already that learning to rank is just an extremely important part of recommendation. So I try to bring this up early on when I talk about recommendations, and we'll talk about how to build personalized learning to rank. You can actually build learning to rank approaches that are both collaborative filtering or content-based. So I wouldn't call this as completely different from the above, but I think it's important in itself enough to bring it up early on. Other things that we can do, demographics. So and this is when you're doing things like advertising, which I didn't mention, it's kind of like one of the legs of sort of personalization. It's not, strictly speaking, I like to make it clear that it's very different to do targeted advertising from recommendation, but using demographic information is something that connects recommendations to targeted advertising. So basically, you're using data about the users, but data about where they come from, age group, and so on. Social recommendations, we'll talk about them. Here you're leveraging the relation between users and whether they're connected and how strongly they are connected to infer whether they're going to like or they're going to buy something. And hybrids is when you combine any or all of the above. And there is a section in my talk where we'll be talking about ways to hybridize recommendation approaches. Okay, questions? No? Okay, so yet another way to look at recommendation is to look at it as an instance of a data mining problem. This picture, which by the way, I now see it doesn't look very well, comes from a chapter of a book. There's a book called Handbook on Recommendation Systems. I wrote a chapter for it, which talked about data mining approaches to recommendation. And I was mentioning that basically the recommendation problem is just a different instance of a data mining problem where you have the data preparation step and you can do things like feature selection, dimensionality reduction, and so on. Then you have the data mining step per se, where you apply all the machine learning methods like clustering, classification, rule association, rule mining, and so on. And then you have the post-processing, which you can do things like filtering, pattern interpretation, and so on. And this is a traditional sort of data mining problem. Now that said, recommendation systems has a lot of other things that I won't be talking about here in this course that are pretty important. And for example, the user interface, right? You can have the best algorithm in the world, but if the user interface is not accompanying and it's not leveraging that algorithm, that approach is not going to be successful. And there are many examples of this. I've seen people trying to get value out of recommendations in a web page, but they're hiding the recommendations on the corner, on the right corner of the web page, and you need to scroll down to see them. So of course, it doesn't really matter how good your algorithm is, people are not going to see them. And then there's some things, there are many things related to system requirements. How does it scale? How efficient it is? Privacy-related issues. Those are some of the things that I won't be getting into, but I just wanted to bring it up. And serendipity, I'll get into a little bit, but it's something that is really not easy to address from a machine learning perspective, because this goes beyond the definition of the utility function that I was describing originally. Because serendipity, what it means, definition is when you find something that you didn't even know that you were looking for, right? So it's an unsought finding. So the idea in recommendations is that we need to optimize for what we know about the user and for maximizing that utility function. However, if we do it in a completely exploit way without introducing some sort of exploration, and I know Deepak spent quite some time talking about multi-arm bandits and explore exploit, right, where you're trying to find the right balance between both things. But the point is that in collaborative filtering, you can have some ways of introducing some controllable serendipity, but it's hard to, by itself, define what serendipity means, right? Because serendipity is something that, by its own definition, is something that it's not based on past data. It's going to be something that is completely an explore approach. Okay, so what works? And I like to start with this before I get into any of the methods, because if you had your startup and you only had that one developer and you had to choose one thing because you can't do everything, what would you do, right? So in the general case, what you would do is collaborative filtering, right? So that's the rule of thumb. If you don't tell me anything else about your problem and I have to choose for one, would definitely go for collaborative filtering before any of the other approaches. Other approaches can be interesting if you have the right way to hybridize and combine it in different scenarios, and we'll talk about them. Things like cold starting when you don't have enough information. Right? But in the general case, collaborative filtering is going to beat all the rest of the methods. What matters in collaborative filtering? So data pre-processing is an important part of the problem and something that you need to be careful about, and you need to worry about things like denoising, removing global effects like user averages or item averages and so on. And a way to do that and to combine it even in a way that you can address the problem better is by doing dimensionality reduction. So things like matrix factorization, SVD, and so on. If I don't have any, again, if I didn't know anything about your problem, I had to go for try something, this is likely to work, I would say use matrix factorization and collaborative filtering. And if you have time, then go to the next step, which is, and then you can add another method, and you could combine it and add it, right? That would be sort of like my best guess. Okay, so let's start with getting a little bit more into the traditional methods, and we'll start with collaborative filtering. By the way, my categorization here between traditional and novel not really meant to mean, strictly speaking, novel and traditional, but this is the classic ones that you would usually try first, and this is a little bit more advanced and introduce some novelties from latest research. Okay, so collaborative filtering, what are the ingredients we have? So we start with a list of users and items. And the only thing we have about the list of items is the opinion, or whether some users liked or did something with those items or not. The kind of data that we will work with can be of two kinds, explicit or implicit. So an explicit is when we do have a rating or something that the user was explicitly giving us feedback on that item, knowing that it was giving feedback on that item. Sometimes the rating of that information that we have is implicit, and I would say not only sometimes, most of the time it's going to be implicit. And that implicit information is actually much more readily available and easy to get. And I will talk about it at the end of the course when I talk about Netflix as an example of recommendations. But again, if I had to choose between explicit and implicit, and this is going to sound weird because some of you, if you remember the Netflix prize, and I'll talk about it, it was based around ratings, which is explicit opinion. I would say you're usually much better off going with implicit than explicit. And there are many reasons for that, but basically implicit information is easier to get. You don't need to get the user involved in the act of recommendation. And second of all is, although it might seem counterintuitive, explicit information like ratings, it's pretty noisy. So just to give you an example, when people rate the kinds of movies that they like, they tend to give, most of the people tend, including myself, we tend to give an aspirational rating. So basically we give a rating really to the quality of the movie and what we would really like to watch. Like if we watch a documentary that is really good and won an Oscar, we'll give it 5 stars. Like, oh, that's a really good documentary. Does that mean that we want to watch that documentary every night? Probably not, right? We're going to be watching comedies that are not so good, but they're a good laugh after a hard day at school or work. And those are the things that we like, but we're only going to be giving that movie 2 or 3 stars, right? So then there's a sort of like contradiction between some of the explicit preference information that we'll get from the users and what the users really want to get. So, and that's the same thing for things like shopping and so on, right? So explicit information, it's a little bit tricky to deal with, and it's much harder to get. That's the other thing. If you want to get big data, with implicit information, you'll get it. With explicit, it's much harder. Okay, so we're going to have some sort of data or information about the relation between a user and an item. Then we're going to have an active user, that person in the room whom we're recommending for, and then we're going to have a metric for measuring similarity between users, and a method for selecting a subset of neighbors. And finally, a method for predicting a rating. So this is pretty easy, right? So if I choose somebody in the room and I say, I'm going to recommend something for you, I'm going to be looking around the room and say, okay, let me find the 5 people that are more similar to you, and I'll pick 5 here. Say, I'll ask those 5 people, like, hey, what do you like? I'll kind of combine that in some sort of average or some way, and then I'll go to him and say, hey, I've talked to these 5 people, and I think that you would really like this. Basically, that's the idea, right? And when I talk to those people, I don't ask them any information about the item themselves. I just ask them about what do you like, right? And that's the basic idea of collaborative filtering. There's no domain knowledge. I don't care. The same exact method could be used for music, movies, books, and I wouldn't change anything about my question. The only thing I would change is I would go to those people and ask them, what's your favorite movie? What's your favorite TV show? What's your favorite song? What's your favorite book? And I would average that and go back and recommend that. So more formally, we identify a set of ratings for the target user. We identify the users that are most similar to the target user according to a similarity function. Then we identify the product these similar users liked. And then we generate a prediction, a rating, for each one of these products. And based on this predicted rating, we sort the items and we recommend the top 10. So this is the basic approach to collaborative filtering. And all the other things that I will throw in later on, including things like learning to rank and deep learning and so on, have a flavor of exactly this same thing. So what's the pro of collaborative filtering? So it requires minimal knowledge, in particular minimal domain knowledge. Right? We don't need to know anything about the items. We can apply exactly the same methods independently of what we're recommending. We don't have to have any internal or structural definition for the items or any even information about the items. And in most cases, produces good enough recommendations. So I said, this would be my preferred method if I didn't know anything else about your problem. Even if I knew about your problem, I would probably end up saying collaborative filtering is a good approach. Now, the cons is that you need data, right? And that's a tricky thing. Going back to the example of, oh, I have a startup and I need to figure out a method to get started with through recommendations. If I think about what I said before, like, oh, go with collaborative filtering, that's easy to say, but to do collaborative filtering, I need people and I need data from those people, right? So that's the tricky part of collaborative filtering. Unless I have users and I have data from those users, I'm not going to be able to bootstrap the system, and I'm not going to be able to give good quality recommendations. The other thing, and these are more minor in some sense, is that I need to have sort of like a standardized way to refer to the products or the items, and this is related to another issue I'll mention later, which is sparsity. If your catalog of items is really, really large, think Amazon, for example, or eBay with millions of products, right? Unless users buy the exact same item over and over again, it's a tricky thing. Then you need to start getting smarter about what you do, because in eBay, maybe not 2 people buy the exact same thing, right? They buy things that are similar, so then you need to figure out what the similarity is, and that's more tricky. In the case of Netflix, for example, do I need the microphone?
Well,
What do you think?
I guess people in the last row will
Okay.
hear you a bit.
Okay, that guy's sleeping.
Well, they might at least wake up.
I think I'm going to wake up that guy in the last room. Okay. So, sorry. I was talking about the fact that if we have a large catalog of items, You need to be able to identify things that were bought were exactly the same. We're also assuming that prior behavior determined current behavior, so that's something that you need to address. If you want to add any information about context, you need to add it in a very different way. So what's the difference between personalized and non-personalized? So I'll get to some numbers now, but the idea is, if I don't have anything better to do, it's always a good idea to recommend the most popular stuff, right? So unless you're sure that you can do better than the most popular, just get started with the most popular stuff, right? Because that's going to be your baseline. And I've seen many, many times, including papers and publications and practical approaches, where people were doing approaches in which they were not comparing at least against the pure baseline of popularity. And if you're building a personalized approach and you're not doing better than popularity, there's something wrong, right? So the basic idea is, if I didn't, again, going to the example of I'm trying to do collaborative filtering for him and finding a good movie to recommend to him, and I had to find the 5 most similar people in the room to do that recommendation, right? That step in itself is a little bit tricky, right? Because I don't know him, so it's like, how can I find the 5 most similar people in the room? So if I don't know enough, the best thing I can do is just, I'll just ask everybody. I'll just ask everybody about their favorite movie. I'll do an average, and I'll go to him and say, hey, chances are they're going to like this movie, because most people in the room like it, right? And I don't know who's most similar to you. So that should be my baseline, and that's a first approach. And if we put that into numbers, and here, what I'm putting here is the mean average error of some typical data sets. By the way, these are, so besides the Netflix data set, which is not publicly available, unfortunately, anymore, Jester, MovieLens, and each movies are publicly available data sets that are used for recommendations. So I think this is an interesting comparison, which is, what's the difference between the non-personalized mean average error? So this is basically the popularity, the most popular thing, and the personalized, right? And you see that there is a difference. So yes, if we do some personalization, and this is, by the way, this is the easier collaborative filtering nearest neighbor approach that we'll talk about. So you can do better than this. But the idea is, by doing personalized, you can do better, of course, than by using the global popularity. But you can do just a little bit better. It's not easy to beat popularity. And this is actually highlighted in this other plot that I have. And this is related to the Netflix price, where here, by the way, this is the root mean square error. So it's comparable, different than the mean average error, but the idea is the same. So I think this is a very interesting plot to sort of like internalize if you're working or if you're thinking about recommendation, which is the idea that if you use what's the root mean square error of a completely random recommendation, this is a 5-point Likert scale, so this is 1 to 5 rating. So if you're completely random, you'll be here. If you use the average, you're going to be right over here. So that's roughly, I think it's 1 point, it's not even 1.1, so it's 1.05, right? So this is the root mean square error. So basically, you're going to be making an error which is slightly over 1 star for the 5 stars, right? So if I predict a 4 for you, it might be a 3, or it might be a 5, but not more. And this is, so this is the Cinematch. This is the original approach that was put out for the Netflix prize, and we told people if you bid this, you'll get $1 million. Look how close it is to the average, right? And the price, which took almost 4 years and a lot of people thinking about and a lot of CPU cycles, was 0.81, a little bit under 0.81, right? So the point here is that it's fairly easy to come up with reasonable recommendations, and the reasonable recommendations can almost be the average ones. And it's pretty hard to get down to be much better than the popularity. However, of course, and the reason that I'm here talking to you, and the reason we gave $1 million for this year, is because this slight difference in the numbers can make a huge difference in the product, right? So every time, and this is old news, right? This was 2006 or 2009, sorry. If I think nowadays, every single A/B test we do at Netflix where we improve this just slightly and we put it a little bit below, has a value of thousands, if not millions of dollars, right? So, but in numbers, if you compare it, it's hard. And if you can do with any domain when you compare the non-personalized versus the personalized, it's hard to beat that thing. Now, when you think about any method that you work on, it's also giving you a good intuition. It's like, well, I'll fit the average into my method, and then all I need to do is have my method improve that average in some way, right? And one way is, as we were saying before, I start with all the neighbors, and then I reduce it to a subset. If I'm able to just remove a few of the bad neighbors, that's going to improve my results. Right? Question?
You consistently get improvements, and whenever you get an improvement in the random in the mean error, you consistently get improvements in revenue.
That's a good question, and it's not as easy as that. And the reason it's not as easy is because it's the mapping between the offline metrics that you optimize in the lab, right? My team is optimizing a number of offline metrics whenever they're doing the machine learning improvements, don't directly correlate with what you see from the users online. So it's a little bit more involved and more tricky. There's not a linear relation. You actually need to build your own regression models from the offline metrics to the online. But directionally, it is true, right? So any improvement you do directionally will show improvement. The question is about how much you need to improve in order to get that delta that makes a difference. Yes?
You recommended collaborative filtering for like starting up as a first step. But doesn't it depend a lot on what features you are looking at? Like you could get, I guess, huge difference if you're choosing the right features in collaborative filtering rather than some other features.
Well, the point I was trying to make is that in collaborative filtering, you don't really need features. Although that was an overstatement if I think about it. So that there is my overall point is like I'm treating user feedback overall as a feature, and I'm assuming that you don't need to do any more feature engineering. Then just take the feedback, the ratings as they are, or the clicks, right? So in that sense, I was my recommendation was independent of the feature because I wasn't even thinking about converting clicks into features. They're just clicks, right? And you can't do much to clicks, although that's not entirely true. Right? I'm not even going to the realm of feature engineering. I'm just thinking about pure click feedback and how to feed that into collaborative filtering. In other approaches, the feature engineering step is much more important because then you do need, if you're doing a content-based approach, there's no way out of the feature engineering step, right? You need to turn a movie into a set of features because otherwise you can't recommend it. In collaborative filtering, you can avoid the feature engineering step by basically saying, well, I just have a matrix of user items and clicks, and I work with that. I don't need the feature engineering step. Although you can still do it. Right? Okay, so user-based collaborative filtering, we have our similar people, we have a weighted sum, we have the target user, and we recommend. So if we turn that into a little more formal, what does it mean? So basically we have a collection of users and that's going to be indexed by I, collection of products on J, and the dimensions here are n and m. So that determines an n times m matrix of ratings. And when I say ratings, again, ratings or clicks, it doesn't matter. We're going to have a number there, or we're just going to have a binary 0, 1. And we're going to have a question mark, and that question mark, we'll get to what does it mean, because that's basically the unknown that we don't know in the matrix if the user did not rate the product or did not buy the product. Right? So basically, again, going back to the previous slide, weighted sum of the neighbors, the prediction for the user is just going to be a combination or a weight of every user and the rating that the user gave to that item. Or we can do something a little bit more fancy, if you will, which is basically using this. This is going to be the rating average, and measure what's the delta of each of the neighbors compared to the average of the item rating, and do, again, a weighted combination of that delta between the average and the and each of the users' rating. So the idea here is I either take all the users that are in my neighborhood and I weight their rating and I predict my rating as such, or, and that's what's usually recommended, or I remove the item average first, and then I combine the deltas from that from that item average of my neighbors in order to determine what is going to be my rating. Okay. Now, the only thing that's missing here is what's this weight going to be? How do I weight each of the neighbors? And each of the weights for the neighbors is going to be based on this idea of similarity. So when I found the 5 people that were more similar to him, instead of just thinking, well, they're all equally similar, and I'm just going to weight equally whatever they said, what I'm going to do is say, well, the most similar person is going to get more vote than the least similar person, right? So basically, we need to have a similarity function which can be computed as a Pearson correlation or a cosine similarity, and that similarity function we can use it for 2 things. First of all, it's going to be used to determine the neighbors. So basically, this boundary, if I'm using, say, I'm going to use the 10 best neighbors. 10 best neighbors are going to be determined by the similarity function. First thing. Second, once I have the neighbors, given that I have the similarity function, now I can use that to weight each of the opinions of the users and plug it in here and use it as a weighted average for the ratings of that neighbor to produce the prediction for the rating of the target user. Okay? Yes?
If you have ratings and clicks, how do you combine both kinds of different?
Hold that question because we'll get there. For now, we have either ratings or clicks, but you can combine that in different ways. And the question is a little bit more advanced than what I'm talking about right now, but we'll get to that question soon. Question?
Isn't it better to use all the users in the space because for some items you wouldn't have any signal from the users for similar to you?
That's a good question. So the question is, why do we restrict the number of users? Because the problem, if we restrict the number of users, then chances that those users have rated all the items become less, right? And when we talk about dimensionality reduction and matrix factorization, we actually hit on precisely that point. One of the problems with this method is data sparsity, and you're going to have problems if the neighborhood or the users in the neighborhood have not rated the items that you're trying to predict. And of course, if your dimensionality of your item space is large, that's going to happen very often. and you're going to have a large neighborhood, and that's not computationally very efficient. So we're now basically hitting all the limitations of this method. This is a method that is easy to understand and easy to explain, and it's not bad, but it has a bunch of limitations, and some of them are becoming apparent just by thinking about it, like, well, is this really going to work? It's easy to make it work in the context of a few users and a few items, right? But if you try to scale it, you realize there are some issues.
What are the practical limits on how sparse the matrix could be?
For the nearest neighbor method to work, I mean, the definition of work is a little bit tricky, right? What does work mean? If it means being better than the global popularity, it can be pretty sparse. I mean, you can have a sparsity of less than 0.1% and still work in the sense that you're going to get better than the global popularity. And of course, it all depends on how you trade off your sparsity against with the number of neighbors you use. And the computational complexity, that's the other problem, right? Like how costly it's going to be. Do you have all the time in the world? And like, I don't care if it takes 3 days to compute, right? But if you start trading off all those things and say, well, I want it to be more efficient, to work faster, to not have to compute so many neighbors and so on, then it gets tricky to make it practical. Okay, so just to give you an example here, I think this is clear enough, so I'll just quickly move over. So so this guy over here is my target user, so I find another user that seems to be similar because she's rated the similar movies, right, or TV shows, and I'm computing here the Pearson correlation, and say, oh, these users are 0.87. By the way, these users, when I say it's not available, is because what's happening here is they don't have any overlapping ratings, so I can't compute the similarity. Okay, so 0.87. This guy's similarity is 1. When you look at the Pearson correlation formula, you'll realize that if the users have rated only one single item and their rating is either both over the average or under the average, the similarity will be 1. If they're over and under, it will be -1. And so that's a property of the Pearson correlation. So in this case, they're both over the average, so it's 1. And in this case, 1 is over the average, 1 is under the average, it's -1. So I have these 3 neighbors, 0.87, 1, and -1 is the similarity to the target user. I combine and I compute the weighted average of the ratings for these 3 users, and I get the prediction for all the ratings. So I basically filled in this row for this user, giving the information that I had for all the other users. Okay? And I'm not saying, of course, I'm not saying this is a great prediction. It's based on very few neighbors and very few ratings. But we have a way of doing something that chances are it's going to be better than if we just took the item average. Okay. Okay, so challenges, I think we've already touched upon several of those. So challenges of nearest neighbor collaborative filtering is, first of all, overall sparsity. Right? If we have sparsity under 1%, in many cases, it's going to be challenged to fill in that matrix and to find those neighborhoods and to do that in a way that makes sense. The scalability is another one we talked about. Nearest neighbors requires computation that grows with the number of users and the number of items. And there can be a poor relationship among like-minded but sparse rating users, right? There's this thing about if I only have one rating in common, it turns out that I get a similarity of 1 just because I happen to have rated that one single movie the same, not even the same, if I happen to have rated above average or below average. So the solution for all these things is the use of latent models, and we'll get to them in a bit. And latent models or mixed factorization, SVD, and so on it's going to be a way of compacting that matrix into a fully dense matrix where we can apply similar concepts, but then in a much more fundamental way. And I know you've already talked about matrix vectorization with feedback, so just to hit on this maybe a little bit more, the basic idea for this is if instead of my matrix representing items, which is going to be a very sparse space, I was able to recommend topics, for example, and it doesn't necessarily need to be topics, but it can be dimensions in my space, like horror or dark movies or comedies or movies that make me cry, right? I could compact that space into something that made sense, and it was much smaller and much denser populated, right? So that's the idea of lived-in models. Okay, so item-based collaborative filtering. I'm going to go quickly over this because it's basically the same, but instead of users, now we're going to do items, right? So I'm going to find similar items, and I'm going to be inferring that if you really like this item, you're going to really be liking items that are similar to that one. Right? And again, the key thing to remember: we don't know anything about the items, so we don't know what they are. We don't even know their name or their title. We're going to be basing our similarity function again on what users did, right? So we're going to be defining the two items are similar if same users like those items. Right? If same subset of users like two different kinds of items, we'll consider that those items are similar. And we only use, again, past ratings or interaction from the users. So we can use the cosine similarity and correlation-based similarities or adjusted cosine similarities. I'm just going to go over this quickly, and we can predict the rating for an item also using a weighted average of the items that are similar. And if we go to the same example that we had before, but now we try to do item-based collaborative filtering. So what I'm trying to do here, my target item is this one, The Walking Dead. So now, instead of having a target user, I have a target item, right? So I'll look for, I'm trying to find the similarity between this item and this item, okay? And I find, in this case, it's -1. In this case, the similarity between this item and this item is also -1. The similarity between this item and this item is 0.86. This item and this item is 1. This one, it cannot be computed because I don't have two users that have rated both Walking Dead and Breaking Bad. And the last one is then the combined weighted average of the ratings that I have and the similarities between the items and themselves, right? So the basic idea is I'm just filling the matrix, but in the other direction. And instead of using the similarity between the users, I'm using the similarity between the items. And to view the similarity between the items, I can use correlation-based similarities, cosines, or weighted cosine similarities. But I'm using the exact same information that I was using before to do filling the matrix in one direction or the other. Okay, so I'm looking at the time and I want to move on, but I'll just do a quick recap of the neighborhood-based collaborative filtering. So we usually have large product sets and the user ratings or user interactions just for a small percentage. And here you have an example in the case of Amazon, and their catalog of millions of books, right? So the probability the two users have bought 100, the two users that have bought 100 books have a common book is 0.01, right? And with 50 and 10, it's going to be 0.0002. So it's going to be really hard to find those two users that have bought or rated comparable things. to even form a neighborhood. That's a real challenge. And to the question of you were asking, like, a rule of thumb of like how many, what's the density of the matrix in order to make sense. So more or less, if you have a number of users comparable to 1/10 of the size of your catalog, you can probably get started. But that's assuming, an interaction model which is similar to the one that I'm saying here. So in the case, going a little bit more into this problem of the sparsity issue, if we take the Netflix data set for the Netflix price. By the way, is everyone familiar with the Netflix price and the $1 million Netflix price? Because I'll describe it a little bit more later, but who is not familiar with the Netflix price? Okay, so just a couple of people, but just 1 minute description. So this was a price that started in 2006. Netflix put out a data set. It was made of 500,000 users and 17,000 movies, and some ratings, actually only 100 medium ratings. 100,000 of ratings to this 500,000 users and 17,000 movies. And the goal of the prize was to be able to beat the Cinematch model, which I talked about before, which was a very simple, actually nearest neighbor based approach. And given that data set, there were a number of teams over 3 years that were trying to beat 10% of the original method. And the way that this was being measured was using the root mean square error. So basically, over 3 years, there were a bunch of teams trying to beat that. And what I'm trying to illustrate here is the sparsity of the data set. So basically, if you take 500,000 times 17,000, you get 8,500 million positions in the matrix, and you have that most of those positions in that matrix are going to be zeros, right? You have very few known zeros in that matrix, and then doing a standard probability filtering based nearest neighbor probability filtering is going to be very challenging. That's why dimensionality reduction techniques are going to be much more powerful. Okay, the scalability, I already talked about this. It's really hard, well, not hard, it's costly to compute the similarity between all the users or all the items in your data set. So the worst case complexity is order MN, which is M customers and N product. In practice, it's a little bit less, but still, it's very costly to compute that similarity. And if you're not going to do dimensionality reduction, something that might help is to use clustering techniques and start with doing some, say, k-means or LSH. I'll talk about that later also. But the idea is you can do some initial grouping of users and then only compute the similarity for the users that initially are similar. Okay, so I'm done with this is just to set the tone of what collaborative filtering is. I thought it was important to at least understand what's the intuition and what are the traditional approaches. And that's something that, again, in practice, you would never implement because it has a lot of limitations. But this is the intuition behind any collaborative filtering approach. And I think it's important to just, take a step back and understand that what we're trying to do is basically only using the data that we have about the interaction between the users and the items, look for similarities in the users or the items, and use the average of those neighbors in order to do the recommendation. And this is what we're going to be doing in any of the other collaborative filtering approaches. Okay, so let's try to be a little bit smarter than that, and let's try to build a model, right? So in the case of collaborative filtering, one, I talked about user-based, item-based. Another partition that you can do is memory-based. Oh, sorry, there's a typo here. So it's memory-based and model-based. So there's these two different options. Memory-based is this idea that I'll use all the ratings that I have and all the ratings from the user and the items, and I'll use those to build the predictions. Model-based is I'm going to first try to be a little bit more smarter about the data that I have. I'm going to build a model, and that model can be probabilistic, using some Bayesian network approach, for example, using clustering, using rule-based, classification, regression, LDA. All these techniques can be used to build a model. And then once I have the model, I'm going to use that model to compute the predictions. Okay. And now we're going to go into the model-based approaches, right? The memory-based approaches is the nearest neighbor approach where I'm not building any model. What if I want to build a model? Okay. And I already explained about the Netflix price, and the reason that I start, I'm plugging this in here with the model-based collaborative filtering is because the Netflix price was a purely collaborative filtering setting, and we learned a lot during those 3 years about what model-based collaborative filtering could do. So the top two algorithms in the Netflix prize were, and that was only about after the first year. So out of the 3 years, we already knew this after the first year, were SVD, and I'll talk about this later, but SVD is not the academic version of singular value decomposition. It's actually a form of approximate SVD, which I prefer to call it matrix factorization in a more broader term. But during the prize, it was called SVD. So that was the root mean square error, 0.89. And then RBMs, restricted Boltzmann machines, I'll also talk about them, form of the advanced neural network. The root mean square was 0.8990. And the linear blend of these two methods, so just a linear regression over using those two methods, gave a RMSE of 0.88. So I think this, I mean, I wouldn't generalize too much, but it is an interesting idea that already back then, it's like two different approaches, a matrix factorization-based approach, a neural net-based approach, were the ones that work best. And if you combine them linearly, doing some kind of, not linearly, combine them in some way, doing some kind of hybrid approach or some kind of ensemble, you're going to improve the result over any of the two. Right? So, by the way, this is still being used in production as part of the Netflix rating prediction algorithm, right? So, this is not a paper that is somewhere and says two methods are interesting and are good. This is actually turned out to be good in production, and it's still being used. Okay, so matrix factorization. Again, I think you talked enough about this with Deepak during his talk, so I'll try to advance quickly, and we'll get to more interesting things. But the basic idea is that that matrix that I had that was full of zeros, in which I had the users and the items, I want to collapse it into something that has less dimensions and it's much less sparse. Right? And the idea of matrix factorization is I'm going to do that by decomposing my original matrix into three. There is a diagonal, so R is the number of factors that I'm going to have in my decomposition. And I'm going to have a user item matrix that is going to be defining the way that the users map into those factors. An item factor matrix that is going to be defining how the items map into those factors. And then a diagonal matrix that maps factors into themselves, or the important factors into themselves, the strength of each factor. And there are different ways to get to this kind of decomposition, but the idea again is that I'm reducing the dimensionality of the item space into a lower space where I have a latent number of factors, and then I'm mapping users to those factors and items to those factors. Okay, whoops. Why don't I see the picture? So, sorry, there was a picture here, there is a picture here. So, and the picture is of a blog post of somebody called Simon Funk from New Zealand. He was, one of the most interesting findings during the Netflix crisis was when he came up with a blog post. I can describe it to you. There's a cow overlooking the sea in New Zealand, and it was called "Try This at Home." And he was explaining an approximate and iterative way using stochastic gradient descent of computing this matrix factorization, right? Or he called it approximate SVD. And he said, hey, I've done this with the Netflix dataset, and it kind of works. Well, it worked so well that he basically went into the top 3 of the, at that point, of the people that were on the ranking for the Netflix prize, right? And of course, because he published it, everyone else started using it and said, whoa, this is really cool, this worked. And that kind of jump-started many teams to get started thinking about matrix factorization, about what they could do, right? And the basic idea is that you can compute this instead of in a closed form mathematical way. You can compute it using any gradient descent technique or any iterative optimization technique, as a matter of fact, and you can use SGD and so on to compute this until you meet some kind of threshold where you cannot optimize anymore. And that was, again, described in this blog post that you don't see here. Now, how do you use SVD or matrix factorization for rating prediction? So it's the idea is quite simple, right? The matrix that we had before, you had some user factor vectors, and you have some item factor vectors, right? So basically, let me go first to the second equation here. So basically, the idea is that you predict the rating for a user and an item, multiplying the user vector times the item vectors. Okay, so in some sense, this is similar to what we're doing with the nearest neighbor approach, where we're doing a weighted average of the neighbors. We're doing something similar, except that now we're doing in a latent space where we have user factors and item factors, right? We're basically multiplying how strong a user is aligned with a set of factors, and how strong a number of items, or the item that we're trying to predict, is aligned with those factors. And we do that by multiplying the U transpose times the V. We add a bias for a baseline, and that's also related to something that I mentioned before, which is like, well, we usually have an average, which will be the item average or the user average. And whatever we compute, for example, in the case of the nearest neighbors, we were subtracting the item average from all the neighbors and then adding that delta. Here it's the same thing. Basically, we have a baseline which includes the user and the item deviation from the average of that item. And then we add this factor here, and we then add the contribution of the user items, the user factors, and the item factors. So it's the baseline, which is the average for both the user and the item, and then the multiplication of the user factors and the item factors. So that's going to give us our prediction. And this is the basic formulation of what a factor model is we're going to be using for collaborative filtering. Again, model-based collaborative filtering using SVD or matrix factorization. Now, Yehuda Koren and others at AT&T at that point, which actually ended up winning the $1 million prize. They came up with a slightly evolved formulation of this. This is what they call the SVD++. And the SVD++, basically the same, except that now here, instead of having the user factors themselves, you have kind of like a decomposed formula where you have you actually have three added factors vectors. The users themselves are not parameterized. They are represented by two things, and that's the R and the U. And the R is the items that were rated by the user, and the N are the items for which the user has given an implicit preference. So the intuition behind this is interesting, and it starts going down. One of the questions that I got initially is like, how do you combine ratings and implicit preferences? So this is one of the ways. Here you have ratings here, you have implicit preferences here. In this equation of the SVD++, you have a way to combine both. And actually, you can combine both even if you don't have implicit preferences. What Yehuda and others were saying here is like, well, beyond the fact that a user has given me a 3-star or a 5-star rating on something, the fact that the user has decided to rate in itself is an important piece of information. So that in itself, the fact the user decided to watch that item versus not watching it, it's important and needs to be encoded in some way, right? And this is the way that it's encoded here in this factor here, where you can plug in the implicit information, right? So this is the user has interacted with the item. This is, okay, has interacted, but then what rating did the user give, right? And this is basically this element here. It's similar to what we would have in the traditional prediction, and this is the other element that is being added, which is the implicit action or implicit preference. Okay, so those two things, so the sort of the gradient descent approach to image factorization, plus the way to include the implicit preference on this formulation of image factorization, those two were important things found during the Netflix rise. The other one was RBMs, and RBMs as a way of introduction. I think you've already had Nando here talking about deep learning, so you probably can skip through some of this. But one way that I like to talk about RBMs first, and then about deep learning second, is like a fourth wave of neural networks, right? We had the perceptrons in the 60s, back propagation that was popularized in the 80s, then belief networks in the 90s, and now in the 2000s we have deep learning. And one of the things that got deep learning started, although at this point it was still not deep learning, was this idea of having restricted Boltzmann machines. So did you, just a show of hands, did you already go through this with Nando? Did he talk and describe what RBMs are, restricted Boltzmann machines?
We covered it very briefly, so there's no harm in covering it in detail.
Okay. Okay, good. So basically, a unit of a restricted Boltzmann machine, this is what it looks like, right? So it's as in any neural network, is basically a unit that can be active or not active. And each input that you have to decide whether that unit is active or not is associated to a weight, right? There's a weight, there is a transfer function that is combining the weighted sum of each of the inputs, and that is fed into an activation function. Right here should be function, and that function has a threshold which decides whether the cell is active or not. This is the basic definition or the architecture of a single RBM unit, right? So again, a score is passed to the activation function here, and that activation function, given the threshold that we have, is going to decide whether that cell is active or not. And there's different functions here that you can use, like a softmax or others. So the composition of a restricted Boltzmann machine is done as a way to, it's actually a way to simplify belief network, in which we restrict the connectivity in order to make it easier to compute the whole network. And the way we do that is by saying, well, there's only going to be one layer of hidden units. You can add, although you can have multiple layers, but the restriction usually stands as one hidden unit. And there's no connection between the hidden units. And the hidden units are independent given the visible states. Actually, this is a way to graphically understand what the RBM network will look like, right? So there is no connections between the hidden units, and there's only connection between the visibles and the hiddens, right? The visibles are what we see, and the hiddens is what is explaining that relation. Sorry, I'm missing another picture here. Yeah, I'll need to fix here. So what I'm missing here that you're not seeing is that there was a paper by Hinton during the Netflix prize in which he actually, I think it's interesting enough that I can probably do it. So it's this paper, Restricted Boltzmann Machine for Collaborative Filtering, in which they were describing a way to use RBMs for the Netflix prize. And actually, this is the picture that is missing in my slides, interestingly. So here, he was showing, or they were showing, basically the exact same idea of the how to use the RBMs to model the different vectors. And sorry, the relation between the ratings and the items. And the idea here is that you have a 5-state softmax unit, and the 5 states correspond to the rating, to the 1 to the 5 rating. And sorry, I think there is another. Oh no, that was the only picture. But oh no, here it is. So here is when you have each hidden unit which has a case of the 5 values of a softmax. So basically, going back. Oh, now it's here. Okay. Oh, there's some rendering problem, I guess. Okay. Oh. Okay. So same thing. This is the same thing that we have here. So in the case of how do we use this for the recommendation? So each unit in the visible layer, as we were seeing before, is an item, and the number of hidden units is a parameter. So in the training phase for each user, think again back to the RBM function and whether the unit is going to be activated or not. So if the user rated an item, the V sub I is activated, right? So there's going to be this V here is activated. The activation states are all the V sub i's that are input to the H. And based on the activation, the H is computed. Now, once you have the activation of what the H activated, you use that to compute all the V's again. And then the state of V sub I is recalculated. The difference between the current and past activation is then used to update the weights here. Right? So this is like you would compute neural network traditionally, where you basically compute the H, then you go back and recompute the B's, and you use that at the end to compute the weights that are being mapped, all the inputs into the transfer function. And then once you've done that, in the prediction phase, when you already trained the RBM, for the items that of the user, the V sub I that are activated, you compute the state of the H of the hiddens, and then the activation of the H is used to recompute the state of the V's of the items. And the activation probabilities are directly used to compute the recommendation of the items, or, for example, to compute the probability of a rating. And that's the other interesting thing, is that we can output, in the case of the 5-stage softmax unit, we can actually compute what's the most likely rating, but we can have a probability associated to each of the ratings, right? We can say, well, for this user, which at 80% probability, we think it's going to be a 4-star rating, but with another 10% probability, we think it's going to be a 5-star rating. We can have a probability associated to each of the states, and in this case, the states are going to be each of the values of the softmax. Okay, and remember, what we finally have in production is an ensemble that combines linearly the RVMs and the SVD, right? Yes.
So before the hybrid, we have an RVM trained for every user, or?
Yes.
And the idea is we have now a lower dimensionality vector that represents this user, which is the edge, the unit, the heading unit.
Exactly. It's a good point. I mean, both in the case of the matrix vectorization, obviously, but in the case of the RVMs, in some sense, we're also reducing the dimensionality, right? When we're training the units that are active and the items that are active according to that user.
What I'm not sure about is how do we make sure that the hidden unit, the first hidden unit across all users, is related in any sense? Because now we will have another model that, given these activations, predicts for all users, predicts a rating. That's right.
No, I don't think I understand the question.
The question is, are the corresponding hidden units across all users have any meaningful relationship among them?
I mean, they have, in the sense that when you're training for a given user, they're going to be sharing the same information that you have. So there is some relation when you're training, right? But beyond that, there is no shared notion of state, right? And that's the point. But of course, because the data you're using is the same, there is going to, so in other words, the RVM that's trained for one user from another user that is very similar, they are going to be very similar. By the way, one of the tricky things about the RVM is that it's pretty costly to train compared to the SVD, for example, because you are doing the process repeatedly for every user. Okay, so another approach, and by the way, I mentioned these two approaches that came out of the Netflix prize. All the others that I'm going to mention now are either not used or newer or different. So these are different things that we can do in the collaborative filtering space that did not come out of the Netflix prize. So clustering, I'm sure everybody knows about the idea of clustering, and k-means is something that everyone has heard of. So the idea is we can cluster either customers or items in some way to build some groups of similar things, similar users, similar items, and then use that for recommendation. The most simplistic approach to clustering will say, well, if I have a number of customers and they bought similar books, I define a cluster where those users are similar, and then I compute the typical preferences for a cluster. And the typical preferences are book 2 is very high, book 3 is high, book 5 and 6 may be okay, and books 1 and 4 are not recommended at all. So this might seem a very obvious thing, but it's a very powerful idea. And it's this idea of, I'm going back to the idea of, it's hard to beat popularity, right? Because we need a lot of effort to recommend something that in a personalized way, it's going to be better than the global popularity. But what if we had a way to restrict that popularity into a group of similar people, like we did with the nearest neighbor, but the nearest neighbor had some practical difficulties and there was sparsity and so on? Well, why not use clustering? So this is a similar thing. It's in this case, however, it's an unsupervised approach. We can just put all the people in the room into a clustering algorithm. We build different clusters. Now, when we have the clusters, we use the popularity-based approach, which is what I'm doing here, computing the typical preferences. But now I'm subsetting it to a number of users that are more similar. And then this is a powerful thing that has shown, in some practical settings to be pretty good. And the idea is simple. It's just build some clusters, and then once you have the clusters, assume that the users in those clusters are going to have similar behavior or similar taste. Yes?
Are you also using some sort of semantic analysis of the content groups themselves?
For now, no. We're only using collaborative filtering. So basically, we're only using the interaction between the user and the admin.
The clustering could also be done with the content, right?
It could, yeah. I mean, some of these approaches could be also used in a content-based manner. But the example that I'm using right now are simply based on the interaction between the user and the admin. As a matter of fact, clustering is a way where you can use to combine both things, the content-based plus. Okay. So one of the only downside, or one of the downsides of doing clustering is that you're assuming that the user behaves as the whole cluster, and therefore, in some sense, you're not doing full personalization. You're just personalizing at the level of a subgroup, right? So that might be less personalized than other approaches. I just wanted to briefly mention LSH. I don't think Deepak mentioned LSH, which is interesting because LinkedIn is known to have used in the past LSH for recommendation. So locality-sensitive hashing is just a method for grouping similar items in highly dimensional spaces. How many people have heard of LSH before? Okay. Yeah. So the basic idea of LSH is you build a hashing function in a way that you're grouping things that are similar, right? And of course, the trick here is like, oh, how do I find that hashing function that is able to group things that are similar? And the main application of LSH is actually nearest neighbor. So now here we're kind of like hitting on one of the downsides of nearest neighbors was the scalability, and it was costly to compute, and it was hard to compute because it was sparse. But one way to address that is using LSH and finding a hashing function, which is usually found in the case of nearest neighbors by concatenating random hashing functions. And then you address one of the main concerns that we have with nearest neighbors, which was the performance and also the sparsity, which is related. So I put LSH here as an approach that is sort of like halfway between clustering and nearest neighbor. But it's a very interesting approach that has found some practical applications. Okay, another approach, association rule mining. So association rule mining is based on the idea that it's based on this idea of defining what's called a transaction. The idea that if you have purchases and you have done a transaction in the past, if you're able to find patterns of transactions, you're going to be able to use those patterns and those similarities as a way to recommend items. Right? So one way people remember about association rule mining is the beer and diapers example. Have people heard about beers and diapers? Yeah. So there's this idea that there was this big supermarket chain that found that looking at the transactions on the purchases, people that bought diapers also bought beer. And then they decided that they should put beers next to the diapers to increase the sales of the supermarket. And the explanation for that, by the way, and then there's a Wikipedia page on that saying, I think at the end it's kind of an urban legend, but it's interesting. And the idea for that was that all the dads during the weekend, they were sent by the wives, hey, go get some diapers. And of course, because they knew they were going to be stuck at home with the new baby and they couldn't go out, they said, well, I'll buy some beers. And they were buying the diapers and the beers at the same time. But that relation between what happened in that particular transaction illustrates the idea of association rule mining. And association rules are used a lot in recommendation for this kind of things, for recommendations on transactions, right? So the recommendation you get on Amazon when you're buying something, say, hey, if you're buying something at the same time, other people also bought this, right? So if you're buying a camera, are you sure you don't need a SIM card for the memory or an extra battery because that one is going to die, right? So this association that happens in the transaction is what association rule mining does. So there is this idea of levels of confidence, and that's what most of the algorithms, like the a priori algorithm, are trying to do two things. First is you're going to try to find frequent item sets, so frequent things that happen together, and then you're going to be defining a level of confidence, and you're going to say, well, if this happened enough times, I'm going to trust that there's a rule here. If it didn't happen enough times, I'm just going to discard it. Because of course, one of the big concerns of association rule mining is that you're going to have so many co-occurrences of things that you need a way to filter them out to the ones that really matter, right? Because some of them might just be spurious relations that seem to have some sense, but they really don't. So they're fast to implement, and the a priori algorithm for frequent item set mining is the most well-known and traditional approach. They're fast to execute. They're not individual, so the interesting thing to realize here is it's a collaborative filtering approach because all you need are relations between user and items, but it's not really personalizing to the user. It's actually personalized, or it's tying the recommendation to the transaction itself, which is kind of like a notion of context, right, in some sense. And again, in shelf layout or in virtual shelves environments like Amazon and so on, it's very popular. And for some transactions in web browsing, for example, they have also been used to try to anticipate if people click here on the same session, what are they going to click on next, and so on. Okay, classifiers. So one not so obvious way to recommend is to build a classifier that basically tries to tell me, is this going to be good for you or is this going to be bad? This is something that I'm saying it's not so obvious because it seems like, can I really classify something into just black or white and use that for a recommendation? Well, it turns out that you can, and it's done all the time, and it works, and you can think about it in different ways. But there are many classifiers that, as a side effect of classifying just a binary classification problem, they output a probability, right? Think of logistic regression, for example. So why not use that probability as a recommendation or as a confidence on your recommendation, right? So that's something that you can do, and you can basically, the benefit of doing something like that is that you can then treat any binary input that you have, which is basically 0 or 1, like, not like, input into a traditional classification scheme, output some classification labels and some probabilities, and use that for your recommendation. And by the way, when we'll get to learning to rank, it turns out that the first approach to learning to rank is using traditional classifiers, like, again, logistic regression or tree ensembles, and so on. So, again, you can either construct an item vector, a feature vector of the item, and then we go into doing content-based using classifiers, which, by the way, it's another possibility. Some of these methods can be used both for collaborative filtering and for content-based. Or you can use the preferences or the click of a user, say click, not click, and feed it into a classifier and say, well, if the user clicked, it means it's a positive label. If the user didn't click, it's a negative label. Then I feed it into a classifier, and then that let the classifier act as a recommendation. Okay. The pros of the classifiers is, well, they're very well known. They've been well studied. They're versatile. They can be combined with other methods, in many different ways, and they can be used as an input to ensembles, for example. The cons is obviously I need a training set, and another con is that they may overfit. By the way, this is not specific only to classifiers. Any machine learning method, including matrix factorization, can overfit, and you need to be careful about regularizing. Is everyone familiar with the concept of regularization? Okay, you should, because that's one of my questions during my interviews at Netflix. So it's a typical question that I used to understand if people know what they're talking about when they describe what a classifier is or what an SVM or what logistic regression is. So anyway, regularization is an extremely important element of most machine learning methods, and we'll actually talk about it. When I talk about tensor factorization, I'll explicitly describe the L2 regularization that we do there. But in classifiers, something to worry about. Okay, so limitations of collaborative filtering. I already mentioned some of this. There's the problem of cold starting. When I was recommending use collaborative filtering for your startup, I then kind of backed off a little bit and said, well, that's really great, but if you don't have enough users at first, it's going to be really tricky, right? Because it's only based on the interaction between users and items. So if you don't have users, you don't have anything to get started with. So you're in a cold start problem. How do you start off using collaborative filtering? Well, you can. You really need to do something else, right? There's something called the popularity bias, which, so I've always, and it's funny because until now I've always talked of popularity as something good. I said, well, it's hard to beat popularity. If you can't do anything else, just go popular because that's a good thing. You can also interpret it in some other way, which is, in general, all collaborative filtering methods, they're going to be starting off some popularity. So it's going to be really hard to go down the tail and recommend something that is really new, really unpopular, really niche. And other methods like content-based are going to be much better for doing that. So, for example, there's a book which actually was a PhD of a friend of mine that he turned into a book of recommending music items in the tail. And the idea is basically that is, if you use collaborative filtering, going down the tail and recommending that song that only 3 people have listened to, it's going to be really, really hard, right? Because all the methods in collaborative filtering are going to be based around finding patterns of usage, and that song has not been used. If you use content-based, you're going to be able to find a different set of patterns. Like, hey, that song although it's only been listened by 3 people, turned out to be very similar to this very popular song by the Beatles that everybody loves. So let's recommend it to the same people. Okay. So the cold start problem that I was mentioning, I want to make clear that people understand there's 2 sorts of cold start, and they're all extremely important, and they need to be addressed in a different way. One is the new user cold start problem. So you have a new user coming to your system, you don't know anything about the user, how do you get started? And of course, if you don't know anything about the user because the user has not given you any sort of input, again, go back to popularity. Just give him something popular, let the user interact, and then as soon as you start getting some feedback, then you can start personalizing and being better about the recommendation. The other problem is the new item problem. And the new item problem is you have your system already working, and all of a sudden you get a new book coming into the system. What do you do with that book? Right? Unless you present it in some way, you're never going to get input from the users, and you're never going to be able to use it as a piece of recommend in a collaborative filtering environment. So you need to have a strategy to get that in front of the users, and there are several ways. One is using content-based approaches that I mentioned before. Other ones is trying to have some sort of explore, exploit strategy related to items that are new and so on. Okay, so I see that I have 5 minutes, but I think I might be able to finish the content-based recommendations in 5 minutes because that's going to be easier, and then I'm going to leave the more advanced methods for tomorrow. So content-based recommendation, the idea is we're going to find a similarity function for items, and that similarity function is going to be based on analyzing the content. And there are many ways that we can analyze or we can have an information about an item, and one of them we can probably have metadata associated to a content, right? So if we have a book or a movie, we have the title, the year, the author, the director, the actor, the genre, things like that. If we happen to be recommending textual things like web pages or documents, we have techniques which are pretty good about coming up with a description of a textual content, right? We can use NLP, for example, and analyze the information on just some language snippets and come up with a description of that document. Or in a similar way, if the content is not textual, we can extract information from the signal itself. There's tons of publications about recommending audio, images, even video by using some sort of like signal processing techniques to extract signals from those documents and then using that description to make the recommendation. But the idea is always the same, is we have a description of the document in terms of features, right? And here, there's no way around the feature engineering step. We need to have features, and then we need to work with those features in order to recommend. And then once we have those features, we can build a model. And we can build the model in different ways. And as I said before when we were talking about the classifiers, a classification technique is a good starting point. I can try to classify the documents into good and bad according to the features, right? And the way, I guess the setting should be pretty clear, but the idea is I have a set of documents, whatever they are, with a set of features, and I have some training examples in which I know they're good or bad for a given set of users, right? And the good and bad can be determined by the rating or simply by the fact that they clicked or they didn't click on a document, right? And I trained a traditional classifier based on those features. It can be textual or signal or whatever they are, and I build a classifier based on that. Just as I was building the classifier in the collaborative filtering approach. And the classifier can be anything. It can be a neural network, naive Bayes, a logistic regression, tree ensemble. The advantages of collaborative filtering is we don't need data about the users. So again, that startup case where I don't have any user, I need to get started. That could be a good step for the first few days while I try to cold start the system. And they're able to recommend new and unpopular items, so go down the tail and recommend that song that nobody listened to. And we can also build them in such a way that we can get explanations on why something was recommended, right? So if the classifier is actually determining that one particular feature has a lot of influence on the model, I can use that to say, hey, I recommend this to you because this particular thing is high or this particular thing is low. And the disadvantages, the main disadvantage is that they can only be as good as the description of the item. So we need to be able to describe the items very well. The other problem is that they can easily overfit, and overfit here I'm not strictly speaking on the machine learning sense of overfitting. I'm saying that you can overfit to what you know about a particular user and recommend things that are too related to the things the user picked before. You can pigeonhole the user into something just by the fact that I clicked on a thriller or a horror movie, and then all you give me after that are just horror movies, because the description of your movie had the tag horror. Okay, so I have to wrap up, but just to quickly go into, so in the case of documents, the easiest thing to do is to build a TF, IDF description of my document. I don't know if people have some background information retrieval, but the basic idea of TF, IDF is that my representation of the document will be a vector in which I'm having the information of the terms, the words that are appearing there, and the amount of information that each of those terms has measured as the uniqueness of that term in the collection, right? So if a word is very common in my collection, and that's going to be measured by the IDF of the term. If it's very common, it gives me very little information. If it's very uncommon, it's likely to give me more information about that document. And the term frequency is how many times that term appears in that particular document. So combining those two things, how many times the word, let's say, laptop appears in my document, and how relevant or unique the word laptop is in my collection of documents, I can build a pretty good identification of or description of that document that can be used as a way to do recommendations. And one of the things that I can do is basically then build a content-based profile for a user, just build a TF-IDF vector for the user, and for each of the documents, then compute the cosine similarity between those two things, and use that directly as a recommendation. So that's the simplest approach to content-based recommendation if I have a textual case. And by the way, I can build a similar, if you replace textual by any other kind of signal, you can do a similar thing. Build your feature space, represent your items in that feature space, represent your users in that feature space, just the same, and find the similarity function between the user and the item in that feature space. Okay, and one of them is the cosine similarity. So I had an example here, but you'll be able to see it in the slides. And I'm going to finish just referencing this paper. Good that actually this one is rendering here. So this is a paper that appeared after the Netflix prize, and two of the people that were on one of the top teams, actually they were second. They published this paper about recommending new movies. Even a few ratings are more valuable than metadata. And this kind of settled one of the most interesting discussions that happened during the Netflix prize. A lot of people were saying, well, the Netflix prize kind of silly because you're only giving ratings on the movies. If we had information about the metadata, and if we knew enough about the title, the genre, the director, the actor, we could do much better recommendations, right? So what these guys did is they went to IMDb and they said, okay, we're going to add all this metadata and we're going to throw it in and we're going to try to improve as much as we can the Netflix price result by using all the metadata that we can. And in this paper, they proved that, just adding a couple of ratings was much more powerful than adding a ton of metadata from IMDb. So really, for some cases like co-starring and recommending some particular items might be useful, but in the general case, collaborative filtering beat content-based approaches. Okay, so I'm gonna leave it here, and tomorrow I'll start with the novel methods. Thank you.
I'm gonna bring you the sheet right now.
Are you? Thank you.
Legal problems. Privacy stuff? Yeah, we still.
Was serious enough to feel that.
Oh, it was very serious. I mean, we had to.
I don't know if it's on the cheap.
Yeah. And it all came out of the research paper, which was there were you're looking at
You're not going to get a response. Yeah. So,
Even take some time.
yeah, I think so.
Alex?
Yeah.
You understand?
Exactly. Yeah.
It's the printer class. I'll come bring it. You might start before I bring it. I'm sorry. Yeah. Left. No, the thing is, left and right was apparently from looking at the audience as opposed to looking at the display. So this will take a minute. Yeah. Well, if you want to read it.
So you want to do it around?
Use the shoot the ball. Oh no, I just used this.
Okay. If you actually, yeah, you can do that.
Let's switch it.
Oh, you need to plug it in. It's so much easier to use this. Sorry. So, yeah, the projector is just doing that transition. Oh, would you rather write on the right or left leg?
Yeah, click on the side.
Okay, good. No, fine. Okay, so projector on. There are ropes, right?
Again, what's the right order?
Well, doesn't really matter.
Really?
Basically, it's I think either way. I mean, it's just
Just bring it down. Yeah,
yeah, basically they shade each other. So if in the end it's displayed like so, it's great, but you would need a ladder, which would be amazingly awkward. So basically, if you can make it so right, great,
And then,
yeah, yeah. But I mean, it's
so
probably, yeah, I mean, that would be great, but it would be probably super awkward. Yeah, you can. Can you stop the camera, please? And maybe do a quick sound check, just. Okay. Good. That's going to continue with the process.
thank you. So, yesterday we started talking about some of mean queries, and you constructed some concepts, but there was very specific to specific problem. For example, in the mean queries, we assume that we have an point, the query was another point to the center. We want to do the sum square distances for this point. We showed that using simple algebra, you can just compute the sum square distances, but it was a bit strange in the sense that it was not exactly just subset of the input. The error was 0, and it was very specific to this problem. And the same with the one center, the K center problem that I showed yesterday. Today I want to show you a technique that how to make also for your problem, for your classifier, your machine learning model, and what are the main problems that we need to challenge. It's kind of a reduction for the original concept problem to some other optimization problems that you need to solve. It might be much easier. So, for example, using this framework, we're able to solve the K-mean queries, the K-mean queries, where the input is endpoints in RD. The query or the candidate state of models is a set of K points. And you want to take the sum distances for every point to its nearest center. And K-mean is the sum square distances. And of course, once we have such a concept that approximates every Q, we can approximate, you can also solve the optimization problem using some planes in the big data model, as we talked about in the previous lectures. So again, we will now try to find a weighted subset, but in a more general way. But we won't use the grid. We actually will still have some kind of weighted points, but And the property will be the same for every set of k-center. The sum of square distances or the sum of distances to the original point and the coset, which is the red points, will be approximately the same. But you won't use the cells in the grid that you used yesterday because the exponential in the dimension is too expensive. You use random sampling, non-uniform random sampling more precisely. So to give motivation for this or other problems, so sometimes because the concept derived from computational geometry, people think that it's mainly good for only for problems in computational geometry, but actually most of the machine learning problems and new classifiers are essentially problems in computational geometry in the sense that you can present a classifier as a simple geometry shape. For example, consider the case of, for example, the Google PageRank, or in general the problem of finding largest eigenvector of stochastic metrics. We want to find x such as ax equal x. We can just rephrase the problem as compute x such as this equals 0. And by just playing with the notation, we can define a matrix P, and we have optimization problem with optimum is 0. Because we know that there is some x such as ax equal x. By putting this phi here, we get this equals 0. So we actually want to solve this optimization problem. And we can solve in PageRank or His algorithm, for example, for the web search, how we're using different P, we essentially need to solve the same problem. It seems to be very a problem in algebra and nothing to do with computational geometry. But actually, there's a simple interpretation for this model. So suppose that we want to find the minimum, the axis of norm 1 that minimizes the sum of square distances. And Marcos epsilon approximation means that it's not optimal, but if one puts epsilon multiplied by the optimal, so the cost is almost the same. And to see the connection to computational geometry, and in general, like in suppose vector machine, there are a lot of other classifiers, including neural networks, that people really don't think in terms of computational geometry. And going to give you simple examples, why, especially when you deal with matrices, essentially everything is about geometry. Because in this case, for example, norm px squared, what is it actually? So it's sum squared inner product between every row in P and x. So take the first row P multiplied by x, take the square, and continue to the next row and so on. So if you think about the hyperplane, when the two-dimensional space is just a line, and you think of the x as the orthogonal unit vector to this hyperplane, then the inner product of a row P and x is just the distance to h, to the hyperplane. So norm px squared is just the sum of square distances between every point to the hyperplane that is orthogonal to the vector x. So in other words, you can say that we are looking for the hyperplane that minimizes some distances, some square distances to the original point, which is exactly the same problem. And more generally, sometimes you want low-dimensional subspace, like in the fixed mining LSA, topic models. So in general, we might want to look for some j-dimensional subspace, or affine j-dimensional subspace, or an affine mean that not necessarily passes through the region. The sum of square distance from the original point to the subspace will be minimized in some sense. So we want to good low-dimensional reduction for the input points. In the concept of process for this problem, again, the input is points, the query is just J subspace, and we want to approximate the sum of square distances to every such J subspaces. So again, input, query, and cost function. The concept is almost the same. Now we just select weighted points. So again, the output, the concept is always points, not lines, not subspaces. But the claim is now when you give me a query subspace, the sum of square distance to the original point to this subspace is approximated by the cost of points to this subspace. So if you do dimensional reduction, you want to find the line or the subspace that minimizes sum of square distances, you can also use the concept. In general, we can also use, for example, projective clustering. For example, instead of k means or j subsets, we want to combine them. So we want several SVD cluster points to several dimensional spaces. For example, in the case of lines, we want to approximate the points by k lines, such as every point goes to the reduced line, which is a generalization of k means or k median in the case of lines, and in general we can talk about k j-dimensional subspaces. Now all this problem can be solved using concepts. Taking this example the last few years, and I try to give you a general framework on how we can construct such corsets. And I will use the same definition from yesterday, which is very, very general. And we use this definition to show that if you have corsets with this property, then you can handle big data, streaming data, and parallel computation. So I use the same cost function that we were able to plug into the tree from yesterday. Just remind you, we talked about general set. Usually this is the points, the input that you want to approximate, or the documents, or whatever. Q is infinite set of queries usually. Cost is what you want to approximate over all the points. And the definition of the cost set is that if I give you a subset from that general set and some error parameter epsilon, you want to find usually a small subset, such that for every query, the cost from P to the query and the cost from the cost at C to the query is approximately the same. So it's not too large and not too small compared to the value that you want to compute. Now, I don't have a general framework for all the problems in the world, but we have a general framework for quite general case. And the case is where the cost function is a sum of some other function. I call it distance, but it's not necessarily a distance function, just for the intuition. Where this is a function for every point, for every query, giving a number. Intuitively, the distance from the point to the query. And what you want to approximate is the sum. So if you want, for example, for k means, this will be the square distance between a point and the newest point in the k center. So you can put this square distance to the zero, whatever, or change the other distance function that you need, like in Richard Gaussian or whatever. Strange function of distance between distributions. And if you have this property of the cost, that is sum over something, then you can prove that if you just take a non-uniform sample going to this distribution, so the probability to choose a point P is just a sensitivity, which means how important this point is. So for all the queries, what is the main contribution? What is the maximum contribution of this query? So what is the worst case? What is the case that this point P contributes most to the general cost? So this means the sensitivity of P. And the term that we'll prove now, and we'll see how to use it for some example, is that if you have this distribution, then all you need to take this number of points going to this distribution, and you have a cost set. So what is written here? This is a sum of all the sensitivities. So again, we hope that this will be less than n, less than the original number of points. This is 1, but we want to find good bounds, so this sum will be at most say log n, much smaller than n. Epsilon is the error, the approximation error, we defined from the previous slide. The dimension of Q we will define now, and intuitively it's related to this dimension of the query space, or practically how many parameters you need to define a query. For example, if you just borrow a point, you need the coordinate to define this point. If you have polynomials, usually the degree of the polynomial. So the complexity of the structure of the queries, I'll define it a bit more formal now. And just to give you a quick example of how we actually use it. So for example, for the k-means, we're able to prove that the sensitivity of the point, of each point, is its distance to the optimal solution, divided by the sum of distance to the optimal solution, plus 1 over np. So Q star is the optimal solution, k means. We talk about square distances, so k median, we talk about sum of distances. And np is the number of points in your cluster. As I mentioned yesterday, if you're in a very small cluster, you'll be surrounded with high probability. But even if you're large cluster, but very far from the center, you also be chosen with high probability. And this dimension is known to be kt. So we have kt over epsilon squared multiplied by the sum sensitivity, which is k. and we get a coset of this size. Now, over the year, we combine cosets with other cosets. For example, yesterday we showed a technique that we took a points P, we project them on endpoint P prime, and then we are able to have a coset for P prime. To get rid of this D, for example, if you have endpoints in n-dimensional space, we show, for example, in the last sort of paper that you can just compute PCA and take the care of epsilon singular vectors, the care of epsilon leftmost singular vectors, and project the points on this care of epsilon dimensional subspace. So you still have endpoints, but like yesterday, now they're in a low dimensional space. And now we apply this technique, this sampling, and this D now replaced by K over epsilon because the points are now lying in K over epsilon dimensional space. So we combine the PCA with the non-uniform sampling technique to have more coset that of size. Note that this is independent, totally independent of the original data, independent of n, the number of points, independent of p, the dimensionality. It only depends on how many clusters you want to approximate and what is epsilon, what is the error. Questions till now? Good. So let's go to business. So I will first show you how to put the claim, how in general, why in general we can compute coset using random sampling, and what exactly we need to bound. And then I try to show some examples of how we compute this this reduction. We use the problem to a very simple optimization problem, and then I will show you how to solve this problem for the K-mean, for the SVD, and hopefully it will help you to solve the problem for your the classifier that you are interested in your research. So let's start. So it might be, again, it might be, so even if you see a lot of equations, I'm not going to cite any complicated theorem in math, in quantum physics, and computational geometry. All I do is just multiplication and move parameters from side to side. Sometimes it will be long, it looks maybe a bit complicated, but there's nothing there. Just, it's not even linear algebra, just high school algebra. But it still took a lot of years for me and for other people to come up with these ideas. But when you see them, think that they're really, really simple, very easy to implement, and I hope that you can use them. So in general, I need to define PW. So P is a set of points from X, and W is just a weight function. So remember, even if your original data is just a set of points, you know, without weights or vectors or chairs or whatever, remember yesterday in the tree, we had to compute coset for the coset. So even if the original data is not non-weighted, the coset is usually weighted. And then during the tree, we want to compute coset for cosets. So usually the input will be weighted. Because if the original data is not weighted, the coset is weighted. And to compute coset for coset, we need to assume that we have some distribution of each point. So we assume that we have a weight function. So P is just a subset from our one set. Usually points in this talk, but maybe in your case tensors or metrics or documents or whatever. And W is just a weight function. Without loss of generality, you can assume that actually the sum of weights is 1. Otherwise, you can just scale everything and divide by the sum of weights. So weight is just importance of distribution over the data. How important is this each point when you compute the cost? And now we want to define query space. Definition, query space. So we see we have F. It's a bit like this that I showed in the last slide. It's slightly different. So for every point and for every query, you have a number. Now this point contributes to the query. And what we wish is usually to compute the cost, which is the weighted sum of distances. So we have points, we have weight function, we have the query, and we define it as the average cost. So go over all the points, take the importance of the points, the first parameter, and then we multiply this by the contribution of F for the point P, the query Q, and we sum. So this is kind of a weighted average on the cost for every Q that we give me. So this I will just call the the tuple P W Q F is called a query space. So when you begin, you try to find a closest for your problem. The first thing you need to define this. This 4 parameter. What is the input? Distribution is the input. Usually just uniform 1 over n for each point. What is the set of query? So it's large Q. And what exactly you want to compute? Distance, square distances, sum of distance to mixture of Gaussians for the vector machine, whatever you want. And these 4 variables will call the query space. And how it is related to our problem, what we want to approximate is the cost. So the first thing you need is to get rid of the multiplication factor 1 plus epsilon and move to additive error epsilon, which is more popular and more useful in statistics and related to the tools that we use. So suppose that we have this property. So we have two, this is the original query space. Suppose that we found a new query space, which would be the core set. So it's work with the same function and the same queries, but the weights are different. They will be sparse. Most of the points will get 0 weight. And this will be the set, will be the subset of P. So choose this with the core set, and suppose that for this space, for every query, we have this additive error. We know what it is. Minus the average cost of the core set is less than epsilon. How does it help? What we want yesterday is to talk about 1 plus epsilon multiplicative factor. And the trick is just observe that by letting FPQ is PQ divided by cost PQ. So just define the function instead of sum of distances, whatever distance, whatever you define distances, instead of sum of distances, define f to be distances divided by the total cost, which is the same as this PQ, the contribution of this point divided by sum, the weight of the point. This is just the total cost. So if I define this function based on this new cost from the previous slide, if I can prove you that I have this property, then we have cost that as we defined before. Why? Because we have, this is what we really want. We want cost PQ minus the cost PQ. We want this, the error between this, the cost of the first point, and the cost of the epsilon this, which means 1 plus epsilon factor approximation. This was also the equation that we wrote on the board yesterday. So 1 plus epsilon approximation means that the difference between these two is epsilon multiplied by the original value. This is 1 plus epsilon approximation. So I want to claim that if you have this, then you have this. Why? Because the cost is just this, right? But the sum is all of the points in the original set. And on the other side, we have this set, the point of the core set. with their weight. But now, what is the connection between this and F? So F is this divided by cost PQ, which is independent of the specific point P. So what we do is just replace this by FP multiplied by cost. This also FP multiplied by cost. So this is just cost PQ. Take it out, multiply by the FP, WP, FPQ minus sum UP, FPQ. Right? I just replace this by F and take the cost out, but this is exactly by the definition cost PQ the average of PW to Q minus the average on the call set using the weight Q. So this was the definition of the average F here. But if I can prove that this is epsilon, again, this is epsilon plus PQ. So what I did was just substitute playing with the notation. So instead of this in cost, we just have one function. And now we want additive error. So we want that this difference will be less than epsilon, not cost. So this is the first step of the reduction. Let's work let's work with F and prove that we have epsilon additive error. And I already told you how to move from percent this to this F. So during the years, a lot of papers will come out with different construction, deterministic construction, random construction. And we show that actually what we really want is process discounts are just generalization of the classic epsilon sample from Vapnik for 71. You probably learned about visit dimension, path learning. I want to show that it's simple reduction. So if you want to know how to do visit dimension and ask the cost sensitivity for the points, then you have a core set. And if in path learning we just talk about uniform random sampling, I want to show you how we can change this to non-uniform random sampling and get a core set. And for this, we just use the definition of epsilon approximation, where epsilon sample, there are a lot of names very related to epsilon net from Vapnik. So a weighted set, this is the definition. A weighted set CU is an epsilon approximation if for every Q in Q we have this. The weighted average is the sum of distances to Q minus the sum of distances to the call set. We wish it would be epsilon, and since usually you have millions of techniques how to compute epsilon approximation, including uniform random sampling, you can go home, but we don't. We have this annoying factor here. So the intuition behind this is, for example, if you think about Chernoff inequality. So suppose that you have minus of number between 0 and 1. And you want to know what is the average number. So we have a technique from statistics, like Chernoff-Hoffing inequality, that says if you just sample something like 1 over epsilon squared points, with good probability, with constant probability, with small constant probability, the average of the sample would be good approximation to the average of the original point. So that's exactly what we're doing before elections, right? We check a subset of people, ask them, did you choose for 0 or 1? And then we decide who will win the elections, right? If you want to know how good was the exam, you just ask 10 friends. All of them failed. You probably also failed. If you just random sample from the test. But in general, if you want to know the average, we can just take random sample. The problem is that this works if the number is 0 or 1. If a single person hasn't been on a vote and you missed it, then it's a problem. So we assume here that everyone has the same sensitivity in some sense. All the people are important in the same way. But in practice, for example, if the number can be between 0 and a million, so this person is 1, can contribute 0 or 1, but the other can contribute 0 or a million, it might be that everything is concentrated in one person, and the error will be large. The error will be epsilon multiplied by a maximum value. So the problem is that when we talk about distances for k-centers, the distance of each point can be very large. We don't want to assume that all the points in the unit cube are something like this, and all the queries are in a unit cube. So in general, these values can be very large, and that's why we have this error. So just using, for example, random sample can give you epsilon approximation, but the error will be too large. So the next tool to get rid of this one, and again, I still don't tell you how to compute epsilon approximation. There are a lot of ways, deterministic, randomized means of papers. The classic way is just uniform random sample, but for now, just assume that you know how to compute this. How can you get rid of this max and just get epsilon here? So this is where the sensitivity comes from. So it was a paper by me, Christian Soler, and Morteza Morteza that showed this specifically for k-means. Definition for sensitivity for k-mean was later by Schulman and Langberg. And then in Stock 2011, we essentially presented this work was with Langberg that we show in general sensitivity for all the problems in the world, how you can reduce everything to epsilon approximation if you know how to bound the sensitivity. And it's amazingly simple. And again, just playing like before with the equation and you get this result. So suppose that SP, this will be the sensitivity, is just the maximum contribution over all the query for a specific point. So I remind you that FPQ was contribution of point divided by the total cost. So this, consistent with the previous slide, is just the maximum contribution compared to all the other points over all the queries. So suppose we have this number, and we just scale the data. So if the point is very important, we give it a high weight, and we sample it with high, so epsilon approximation talking about uniform random samples, so we just duplicate the point a lot of time, and then if you do uniform random sample, we choose it with high probability. This is intuition that we could take points that are very important, just duplicate the minimum of time, so then we can say just take uniform random sample again from this set. So this is SP, so the new weight for the set. So we have a weight function again. We define it to be the original weight, or forgotten T. T is the sum. C is the sum of all the sensitivity, all the points multiplied by the weights. So T is the sum of weighted sum of this SP. Again, it's both of them independent of a specific query. You can compute it before you get any query for the cost of construction. These two numbers, S and T, S for every point and T as the sum. And we define this to be SP over T. So what is your sensitivity compared to the overall sensitivity, the total sensitivity, multiplied by the original weight. So if you, it's very important in the beginning, we still want to give it the credit. So this is the new weight function on the points. But again, we want to change the weight and probability, so that for every query the cost will still be the same. So we need to change also the function. We define a new function. So again, this is a function that we can put in a query space, and we define it to be like this. It's just the original function, the original function divided by SP, by this value. So if I give you a query, it's still computing the original cost of your point of the query, we divide it by SP, which is the importance of this point. And note that the weight, here SP is above, here SP is below, so when you compute the weighted F, they will cancel each other. So next thing is suppose that CU is an epsilon over T approximation for the new set. So it's the same set of points, but a new weight function, the same set of query, and a new cost function for each query. What you can say about C? And the claim is that you have the property that we want. So every Q the average weight to a query for the original point minus T multiplied by the average weight of the core set is epsilon without the max here. So actually this is the corollary. There's not too much to prove here. Just plug in the parameters and let's do it together. So suppose that we fix some query, and by the way that you choose the weight in the new F prime, we get that WP FPQ, which was the original cost for a point, is exactly the same as T, which is kind of a constant, multiplied by W prime P F prime PQ. So we just play with the W and F prime, so the sum is essentially the same. W is smaller, F is larger, but everything cancels out. So the cost is almost the same up to some factor of T that we can pay in the core set. So we have that this cost equal to the cost of F prime. Okay, so we can forget about F, and now I try to bound this one. But what is this? So again, from this we have that what we actually want to have is this value is exactly the same as the error from F prime. So instead of bound this, we just need to bound this. But we already know that CU is an epsilon approximation for this set, for PW prime Q. So what is this? So we have that T, this value is less than, I keep the T, but this is epsilon max. This is the definition of epsilon approximation. We have epsilon, but we still have the annoying max here, right? Right now the max is the same queries, because we didn't change the query space, but now it's about F prime PQ. And now you can understand why I define F prime the way I define. So F prime has the property that the sum is preserved. Now suddenly the maximum is only 1. So, since actually we have, sorry, this was epsilon over t offset. So this is just epsilon over, and this is just less than epsilon, because again, by definition of prime, this is 1. So again, the reason why I define f like this is because when you look about the definition of f prime here, f pq sp, it must be less than 1, because sp is the maximum possible value of all q. So I don't know q in advance, since sp is the maximum of all q, f prime is always less than 1. So the error max that I have here now disappeared, and we have epsilon error. So this was essentially a reduction within the original data. I move from cos to this to f. Then I move from f to f prime, and then I just need to compute epsilon approximation for f prime. So there are two problems. How can I compute epsilon approximation? Can we compute it efficiently and small? This is very easy. This is related to visit dimension and random sampling usually, and we have so many results in the 70s. We have visit dimension precision trees, neural networks. Never classify one, just rule it and define the visit dimension. So this is the easy part. The main part, the hard part, is to bound this SP. Sometimes just take a few minutes, someone come with a problem. After a few minutes we have SP, and it's not clear that we have a paper because it's so easy. We have a coset. So now if you have a bound SP and you know how to compute this dimension, you have a coset. If the sum of the SP is not too large, sometimes it takes a few years. For example, K-means with outlier, we spent 2 years in Caltech just to bound the SP, and saying that now we do some coset for Fourier transform. And again, it's sometimes extremely hard, but you don't have epsilon here. It's much elegant and smaller optimization problem you can deal with, and then just plug it to this system. So there are still two things we need to do. So I want to just cite the term of how you actually compute epsilon approximation, and then give you examples, probably we'll continue tomorrow, how to actually bound sensitivity for problems that they showed, like K-mean or SVD or matrix approximation. So usually, again, there were a lot of very long papers that describe how to do this. Now, after this, you just shoot 2 lines of proof how to bound the sensitivity. Drag it to here, and you have a new concept, and instead of you reading a lot of very long papers of me and my friends using this kind of framework. So I have 10 minutes, so I'll give you a hint how we define epsilon approximation. Is this the right thing to do? I don't know. So let's just address this one and see how we can compute epsilon approximation. So in our I suppose to convince you that for a process, all you need to do is find SP and compute epsilon approximation for the new set of function f prime. And the epsilon approximation might be easy if you check it with random sampling. And this is the result of Daphne. I want to know that this is an upper bound and not lower bound. So there are problems that the visit dimension is infinity. So you cannot use this technique. And still people show that you can get epsilon approximation. So, for example, if you want a deterministic algorithm, this might not be the best tool for you. So it's just an upper bound, not a lower bound. You might find other technique, but the reduction is only for epsilon approximation. So I need to define the dimension of Q. That's what I mumbled in one of the slides. It is time to define what this means dimension of our query space. And for every positive R, we define the range of this R. So the range QR is how many points. So take a query Q, for example, point, and take all the points of distance at most R for this query. So for example, if the query is a point, you have radius r, to cover some of the point or not from the input. So the range of QR is just a set of points that you cover. So again, in general, we don't talk about points in balls. We just have some distance function f, and you want to check how many points this cost, the f, the weighted f, is less than r. So this defines the range QR. And the dimension now of Q, or more precisely of the curved space, we have P, W, Q, and F, is the smallest, usually integer d, such that the following hold, for every subset in P, the number possible range where Q is in Q is positive or non-negative less than S. What is the intuition behind this strange definition? So suppose that you take n points how many subsets we have from n points? Order of. You must help me with this. This is easy. How many? You have n points. How many subsets? You have n numbers. How many subsets you have in a group of n items? 2 to the n, or more or less. So we have 2 to the n subsets. But what if I ask you how many subsets you have, so that you can cover this subset by a ball or a circle? So, for example, these points, this set can be covered by a circle, but you don't have a circle that covers only this point and this point. So not every subset can be covered by one ball. So how many subsets you can define so that each subset is exactly separate from the other by some ball? And you can prove very easily, and again, this is the result of this dimension pack learning. For example, in this case, you have something like, so if you have in d-dimensional space, or for example, if you're in two-dimensional space, you just enter to some constant 2, 3 at most. Why? Intuitively, for every set that you can cover by a ball, you can always move the ball so that and scale it so that the set, so that the ball will intersect 3 points. You can see you move the ball until you intersect 1 point, then rotate it until you intersect the other point, then scale it down until you intersect a third point. So every point, every set that is covered by a ball, you can always find a new ball that covers this set and intersects 3 points. But if every set has such a representative point and we have about n points, so we have about n 3 subsets, which is order of n to the 3. In d-dimensional space, we won't have 3 points, we have about d or d plus 1 points. So the basic dimension is O of d. This intuition is what's hidden in this equation. For every subset, the number of covers that you have is the number of points in the group to the d and not, for example, to the n. More practically, intuitively, d is just how many points or parameters you need to define a classifier. For example, to define a ball in two-dimensional space, you need the center, which is 2x, y, 2 parameters, and the radius, which is r. So you get d equals 3. In d-dimensional space, the center is d parameters, so you need d plus 1 parameter. Now, this is not true. There are counterexamples when this trick doesn't work. Intuitively, practically, usually this is the case, the number of parameters you need to define a query. But Again, if you want to prove things, you must use this definition. So now, why do we care about this dimension? The reason that we care is that after you decide what is the dimension of your problem or prove it, now all we need is to take random sample, uniform random sample, and the size of this sample is just depend on the error that you want epsilon and this dimension. So this is the main motivation for defining this dimension, or dimension, which is kind of generalization for this dimension. So this is the famous theorem. This is the main theorem of PAC learning. It was recently improved. I give all the credits in the last talk, but this is the main theorem. Again, I write it in our notation, but I did the same as the original one. So we have a query space. The dimension B. So now we know what is the dimension. Now just take a uniform random sample. This is kind of the classic concept. Let's see the uniform random sample where P in P is sampled with probability proportional to its weight, or proportional to the weight. So if all the points have the same weight, then it's just 1 over n uniform sampling. Some points are more important, just use this important. And we define a new weight at the point in the call set we have the same weight, 1 over the size of the call set. Then, if you will sample at least, the question how many points you want to get an Epsilon approximation, and the claim is that if you sample D, which is the dimension, plus 1 over delta, that delta will be the probability of success. So what we get is the probability at least 1 minus delta C is an epsilon approximation of the query space. So epsilon approximation means for all the queries in the world, you're good. You have only epsilon error. So the probability here is in the same time for all the queries. This is something very important. It's not that if you give me a query, maybe I'll be good, maybe not. Because you have an infinite number of queries and I will fail in some of them. No. For all the queries in the world, I'll give you an epsilon error. And the probability this is true for all the queries in the world is this 1 minus delta. But it's not for each query. This gives you the, so this is, you have here the error that you want, epsilon, delta probability of success, note that it's log. So if you just take, log n points, the probability of failure is about 1 over n. So if you just pay very little, you get very, very high probability for success. D is the dimension, and now we can combine this. So let's just summarize what we have till now. So we begin with some distant cost function. So we begin with this, and this we define cost. Then we define f, which was just this divided by sum of distances. From this, we define sp,
was the sensitivity. Using ST, we define a new function f prime and w prime. And then we show that we just need epsilon approximation. And for this, we show that we just need to take uniform sample and uniform up to the weights, but now based on this new function. So we change the weight of the function and just take uniform random sample from this test. In the end of the day, the code looks like this. We find some with approximation for the optimal solution, write S as the distance for each point to this solution, maybe scale, and take in weighted sampling based on this function. Weighted sampling is, for example, in Meta, we just weight sample or something like this. So there's one-line Meta function that just give the weight, Meta already will scale to you, and then you can take a sample. So it's we end up with 3 lines of code. I'll try more on Friday talk about how we actually implement this and show some example codes. Amazingly easy. I think it's a good point to stop today. I'll try to answer questions either online or offline now. Any questions you want to ask right now? Yes.
This is the class log one.
Yeah, class. It's a new result actually. So Vapnik has a wiki result 2 years ago. I don't remember the names, but I'll give the credit. You get rid of some log. This was not the original Vapnik result, but it's a bit newer improvement in the recent years. Yes?
So are you sampling probability directly or double dash?
So here there is no W dash, right? So this is self-contained. Just give me a query space with W, and then I'm going to W. Of course, in practice, after you go to this step, W will substitute W prime, and F will be F prime. Okay, I'm sorry if it's confusing. This is self-contained thing. Questions? Great, so if you want to talk to me about specific problems that you think that you might have caused for, I will be glad to help. I'm here till the weekend, and you can just send me an email. Let's get a partner. I always talk with some of you, and I'm very excited about this. Thank you very much.
Yeah, it's actually a problem. Okay, what is the
Who's quick matching? Yeah.
We have some error. The sentence is exactly the same. But it's not.
Oh, I thought
I have the yes. No, I bought this one. No, I got mine. I got mine like more than a year. Obviously, I just bought it.
And you have query, right? So this is your
Now we're going to Thailand for Christmas.
Yeah, query.
Yeah, or we could do
Scan and then
Yeah, unique is good too.
Let's not do something else. Something else. Let's hope it's not. Well, this one, that's a very, fun, you know,
Especially this was laptop, you know, there's so much tracking stuff in it that it takes it.
We write the day.
I mean, it's like. Right. Yeah, actually, they call that.
Square sequence.
I'll be right back.
So if you combine, so it's in the